let's look at what we have first. So we have the year 1968. So I have 5,000 people living in there. 5,000 people living in 1968. And in 1992, how many people did I have? 12,000 people, right? So we're starting in 1968. We have to have a starting point. So this 1968 is like year zero. And how many years is that from 1968 to 1992? 24 years, right? So in 24 years, the population went from 5,000 to 12,000. So we need that to get started. So we have an initial amount. So the initial amount is going to be from 1968. So remember I told you the initial amount means when your time is zero, that's how many people are living or what the population might be. So in this case, it would be at zero, we get 5,000 people. So this is going to be my n naught here. We'll need the same equation again. And so after 24 years, I have 12,000 people. So my n of t, or my n of 24, is going to be 12,000 people. So I'm going to put in 12,000 for this one here on this side after 24 years. And n naught is 5,000. That's the initial population. I don't know what k is. We need to figure it out. That's what part A is about, finding the growth factor. So k and then t, right? So 12,000 corresponds to 24 years later. So 68 plus 24 is 92. So I need to put in 24 for that. So you look at the difference between the years and that tells you the time, basically. So I have 12,000 equals e to the 24k times 5,000. I forgot the 5,000. So this should be 5,000 here. I just didn't write it by mistake. Okay, so this is what I want to solve. So if I divide both sides by 5,000, then it's not there anymore on the right side. But if I do it on the right side, I have to do it on the left side too. So if I divide 12,000 by 5,000, I get 12 over 5 as a fraction in lowest terms. And all I have left on the right side is e to the 24k is my right side. The 5,000s cancel out. So I have to take ln of both sides, just like I did in this problem. We took the ln of both sides of the equation at this point. Ln of a half and ln of this side here. So if I take the ln, we know that ln of e cancels out. So all I get is 24k. In this example, it was 6k. 6k this time 24k. So I have ln of 12 over 5 equals to 24k. So if I ln 12 over 5 on my calculator, it's going to give me a decimal number. So ln of 12 over 5 is 0.875468737. Now, if I divide that by 24, I'll have k isolated, which is what I want. So if I round to 3 decimal places, I get k is approximately 0.036. 0.036 approximately. So that's part A. So part A was just to figure out the growth factor. So notice that it's positive. right? Because I'm dealing with population growth. In the last example, it was negative because it was exponential decay. See, it was negative 0.1155. Here it's positive 0.036. Right? So that's part A. Part B. So what if I tell you to model this? So you're going to model this equation using the model, right? This equation again that we have. N of t equals n naught e to the kt. But we know the initial amount, right? So n naught was 1968. There were 5,000 people. So we say n naught is 5,000. And the k value, we just got that a minute ago, is the growth factor. So that was 0.036. So to model this, all I have to do is plug in those values, just like with the caffeine problem. So I have n of t is equal to 5,000 e to the kt. So 0.036 t. That's my model, exponential model for this. All right. Okay, so that's part B. So again, a model we use to make predictions about stuff. So in this case, we're looking at the number of people that are going to be living in the city. We're interested in seeing how that behavior goes as time goes on. So for part C, I ask, how many people will be living in the city by the year 2040? 2040. So that's still 19 more years from now, but we're not talking about now. We're talking about from 1968, right? So basically, you're looking for the number of people in 2040. So the time is going to be 2040 minus 1968. How much time has passed since 1968? Well, 72 years, right? So 2040 minus 1968 is 72. So people born in 1968 are going to be 72 years old by then. I'll be 56 approximately. But yeah, so this is like our starting point here, our reference. Okay, so I'm asking how many people. So I'm looking for n of 72. That's my question mark. I don't know. So I need to put in 72 into that equation. And also here too. Wherever I see a t, it has to get plugged in. That'll tell you the number of people. So of course, it's population growth. So I'm expecting that there's going to be a lot more people. There's going to be a lot of people, right? 72 years is a long time. So again, we know E is approximately 2.71828. And I have 0.036 times 72. Plug it in for T. Okay, so 2.71828 to the power of 2.592. That's what you get when you multiply these numbers together to the power. So 2.71828 is E. So if I raise that to the power of 2.592, I get 13.35643454 on my calculator. So again, we have to do order of operations. So we do exponents before we multiply, as we've seen earlier today. So what do I get for this? I get approximately 66,782 people. the population by 2040. So you started out with 5,000 in 1968. You had 12,000 in 1992. Now in 2040, you have 70,000 people, almost 66,000 people. So it is growing. It's going up. Okay. So what if I ask you to go the other way around? What if I tell you that instead of giving you the time and having you find the population, I give you the population and I have you find the time instead? That's what part D is about. So what if I ask you, in approximately which year will there be 100,000 people living in the city? So this is like the population that I gave you here, 100,000 people. So we're already at 66,000. So 100,000 is a little bit more. So you might as well see, when is that nice round number going to come up? How long is that going to take? So for part D, you need to do the opposite. So I tell you that N is equal to, 100,000 people. So you need to figure out the time first. And then once you figure that out, you have to add that to 1968. So I'm asking about which year that's going to happen. Okay? So in approximately which year will there be 100,000 people living? So you have to calculate the year that that's going to happen in. All right, well, we have an equation to work with. So what's our equation? We have N of T is equal to 5,000 e to the 0.036 t is our model. I'm going to put in 100,000 for this, and I'm going to solve it for t. I'm going to figure out t first. So e to the 0.036 t is what we got. All right, so I'm going to divide both sides by 5,000 first. So 100,000 over 5,000 is going to give you 20. 20 equals to e to the 0.036 t. So I have to ln both sides of the equation. So we're in the same spot as we were for the last couple examples. So if I ln e, I know that's going to cancel there. So I'm just going to have the power. And I have to also take ln of 20. Whatever I do to one side, I have to do to the other. So I'm going to get 0.036 for this t. So I need to solve for t. So what am I going to do? Well, divide both sides by 0.036 is what we're going to do. And then I'll pretty much have the answer almost. So ln of 20 divided by 0.036 gives me that t is approximately 83. About 83. It's a little bit more, but let's round it to 83. Okay, so that's the number of years after 1968. After 1968. So again, I told you on the top that whatever we get for t, we have to add it to 1968. So where did I put that? Here. So we have 83, right? So 83 plus 68, 1968 is what? Approximately 2051. Year 2051. So that's like 30 years from now. It's 2021. So in 30 years from now, we expect that there's going to be 100,000 people living in the city. We started out with only 5,000 in 1968. So 83 years later, in 2051, we expect 100,000 people. 20 times as much, basically. Again, we do this to make predictions. That's what equations and mathematical models do help us make predictions about things, reasonable predictions. Any questions? Does it make sense? Let's talk about the logistic model.